Plate tectonics. This is probably something that you're familiar with, just as many things are in earth science. There's a lot of review from middle school, which is good for you because that definitely makes this class a lot easier. So let's go ahead and take a look at our tectonic plates. So within geology, we keep talking about how geo means earth, and you already know, but there are different parts of the earth. Each of these parts are defined by their composition. So the first thing we have is the crust, and you need to be writing all of this down. The way that we know something is the crust is it's the very thin layer, it's very rocky, and it's the outside. So you have the thin, rocky outer layer as the crust. You have two types of crust. It can be oceanic or it can be continental. So if you look at this picture up here, right here where my X is, we have the ocean, and right here we have continents, we have land. So when we're looking at our crust, you either have crust that is on the ocean floor, or you have the crust that is the continents and the countries that we live on. You don't need to write down this bottom thing, but oceanic crust, which will come up in just a second, oceanic crust is typically about 7 kilometers thick, which is about 4.3 miles, just to give you a general idea. The crust is not going to be the same thickness everywhere you go, though. There are certain areas, such as the mountains, where that crust is obviously much more thick because you have a very tall mountain on top of it, versus if you have certain places on the ocean floor, that crust, such as this one, is going to be a much more thin crust. Because it's so far down to sea level. So 4.3 miles is considered very thin for the crust. So it's not that you could easily dig through to the mantle just to, if you wanted to dig your way all the way down into molten rock. I don't know why you do that, but you could not easily do that. I don't know if you even could do that because the amount of rock that you would hit as you go, and also the amount of heat and pressure, that would take so much equipment that I don't think we have the technology to do that. Plus, there's no reason to. So, but that is the crust. It's important that you know that there are two types, oceanic or continental. Just because the ocean has water on it, remember there is land under the ocean water. That's why there is oceanic crust or there's continental crust. That's going to come up very important here in a little bit. So the next part of the earth is the mantle as we work our way down. The mantle is the majority of the volume of the earth. It takes up 82% of the earth's volume. So looking at these pictures, you can see just how thin the crust is compared to the mantle. And also you can see how small the core is compared to the mantle. You could think of the earth kind of like an apple. The skin or the peeling on the apple would be considered the crust. The actual meat of the apple would be considered the mantle, and then where the seeds are would be considered the core. And so the majority of the apple is made up of the meat of the apple, not the skin or the core. And that's exactly how the earth is. The mantle is going to have solid rock at the very top of it, but it's going to be liquid at the bottom. And so why do you think it would be liquid at the bottom? Well, the core is really, 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 really hot. So it's going to melt all of that rock. So the closer you go down to the core, the warmer it is. Therefore, the more melted the rock is and the more liquidy that it is. And again, this is magma because it's below the Earth's surface. As you get further away from the mantle, temperatures are cooling off because we know the crust is not hot. So temperatures are cooling off the closer and closer and closer you get to the crust. And so some of that magma is beginning to solidify a little bit. Now, it's able to move a little bit, but it is still just considered to be rock. So your mantle has convection currents in it, and that should make sense because we know that that convection is caused by differences in temperature. And here, we obviously have a difference in temperature. That really hot magma by the core is going to move up, and then as it cools off, it's going to become more dense, and that's going to cause it to go back down. So you have convection currents that are occurring within the mantle. So really hot by the core, so it goes up because it's less dense. As it cools off, once it gets towards the crust, it's going to become more dense, causing it to sink. And so that's where you have those convection currents, and that is occurring all throughout the mantle. And next we have the core. The core is actually split up into two different parts. We have the inner core, which is the innermost part of the Earth, and then the outer core above it. So the outer core is going to be a very liquidy layer, and you don't need to write that down, just write down the bolded parts. And just to give you an idea of how thick the inner core is, it's 1,404 miles. So that is extremely huge. Yet, if you think about it, the core is a very small part of the actual Earth itself. So that, I think that's kind of interesting because it just gives you an idea of the size of the Earth as is. An important thing to know about the core of the Earth, especially the outer core, is that it has a metallic field that is generated from it. That we are definitely going to come back to in a couple of units. So that's a key piece of information to make sure you know. So the outer core does produce a magnetic field. For those of you who like your cell phones and you like having a GPS and all of that stuff, well, that is, you can thank the fact that you have your magnetic field within the Earth for that. That magnetic field is also something that is just keeping us alive. So that's kind of a big deal as well. But we will get to that later. The inner core is going to be a lot more solid, and it has very, very high temperature and pressure. The reason the core of the Earth is so hot has to do with the amount of pressure that is within it. The temperature and pressure are closely related, but it's mainly made up of nickel. So the most important thing to know about the outer core is that it has a magnetic field. And then the most important thing to know about the inner core is that it is composed of nickel. So there are your facts about the inner core and the outer core. So inner core nickel, outer core magnetic. The mantle has convection currents because of its differences in temperature, is the main part of the Earth, or main volume of the Earth. And then the crust is made up of two parts. You've got the oceanic crust and the continental crust. So those are all the key points of all three parts of the Earth. But let's keep going. And I know some of you are probably getting a little bit antsy, but we do have a little break coming up in just a minute, so hang with me. So Continental Drift. You've probably heard of Continental Drift. That is a theory that was proposed by, by this handsome fella up here. His name is Alfred Wegener. He is, I think, German from his last name, but Alfred Wegener, good old Al, came up with this theory. And he basically was saying that at one point, all the continents were joined together into one single supercontinent. And we know that continent as Pangea. Very good. So that is actually going to be our next slide before our break. But make sure that you do know Alfred Wegener was the one who came up with this theory. And that continental drift is simply saying that at one point they were all one giant continent, but over time they drifted away, hence continental drift, and they had a lot of different shapes. Pangea is just one formation of many, many, many that occurred. That's just the most famous one that we always talk about, but you can go back and look up all the different formations that the continental drift had. So Alfred Wegener, all the continents were once joined together. I'm going to move on because you don't need to be copying this word for word. You can kind of come up with it in your head and then write it down from there. So let's keep going. Pangea. Pangea was the one form of continental drift that's most popular. It occurred about 500 million years ago. That's what MY stands for. So 500 million years ago, we had Pangea. The continents started breaking apart around 200 million years ago. So they were together for a very, 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 very long time. And then North America and Africa were actually together, which you can hopefully tell from this diagram. And they split about 135 million years ago. So all the continents kind of drifted at a different rate. Some stayed together a little bit longer than others. But that is just a little overview / reminder of Pangea. And I will give y'all a second to finish writing that down, and then we'll move on and we'll have a break. Yay! So if you want to go ahead and pause the video now so people can finish writing and then go ahead and do the card sort. Actually, don't do that. I lied to you. Let's make sure everybody's done writing so I can get off of this slide and then do the card sort. Okay. I'm stalling. So I hope you're all done writing because I'm moving on so that we can keep going. If not, you can pause and then play again so that the slide is off. And moving on. Okay, if you did not finish getting the notes, get the notes from a friend. But while that happens, we're going to do a card sort. So you can go ahead and pause now, for real this time, and pass out the card sort. Okay, hopefully you all enjoyed your card sort. This picture should look somewhat similar to part of the card sort. As you saw, there were pictures of fossils and mountains, and one way that could have helped you and your partner put the card sort together faster was to line up the pictures of those fossils, because that actually is one of the forms of evidence of continental drift. So there's 4 main forms of evidence. One of them is the shorelines. The shorelines look like they fit together. Within your card sort, that place that it was most obvious to see that was with South America and Africa. It was pretty easy to see that they looked like they went together, kind of cookie cutter. Now, you've got to remember that we are looking at the continents from 300 million years ago. There has been a lot of weathering and erosion that has occurred on the shorelines, so they're not going to be absolutely perfect fits. So as you were working on it, it didn't look exactly like it fit perfectly, but they should at least look like they went somewhat together. So shorelines looking like they fit together is one form of evidence. Our other form of evidence was fossils. This is something like, say you have this little lizard, this little guy down here. Say he can't swim. Well, if his fossils are found in South America, and only South America, and then the only other place you can find it is in Africa, and we know that that type of animal is kind of restricted to a certain location, then what common sense tells us is, well, since that lizard couldn't swim across the ocean, it had to have one point been able to walk across the land to get there. And so there's lots of different fossils that show us that, not only with animals, but also plant fossils that tell us, well, at one point, all of these plants lived in one little clustered area, but we see a cluster of them in Antarctica and a cluster in Australia. And the only way that could have made sense is if those continents were together and at very similar latitudes, because plants can't just live anywhere. Next, you have mountain belts, or your mountain ranges. And I've got a good picture of this on one of the next slides. But mountains we know can't move. And you have mountains that will start forming in one country and then pick up again in a completely other country. And we know it's the same mountain ranges because of the rock types and the ages and all the testing you can do. So that again tells us at one point they were together. And then you have ancient climates. So how do ancient climates tell us anything about continental drift? So what does that even mean? Well, ancient climates are really referring to like your, some of you may be thinking of the ice cores, but really glacier evidence is what we're looking at. As glaciers move, they shape the landscape. And so we can see that there are evidences of glaciers in places that don't usually have glaciers. And so we know they had to move throughout the latitudes in order for that to have occurred. I do want to point out that climate and weather are 2 different things. So we're not looking at the weather nowadays and saying, oh, that's evidence of what's going on. We're talking about evidence of ancient climate. So what was going on for a long period of time in that area. So for instance, it being extremely cold, that's how you're going to get your glaciers. So let's look at some of these pictures. These are your mountain ranges. This is what we look like now, and this was then. So these mountains formed at one point all in one big cluster. And we can see the Appalachian Mountains within the U.S., they form here, stop, and then they pick up all the way over here again and keep going. Well, the only way you could have the same mountains with the same rock and all of that stuff is if at one point these were actually connected. And this is also interesting because right here, which I'll show you in a little bit, we have what we call a divergent boundary. And this divergent boundary is what means the Earth is dividing. and new ocean floor is being made there. So that's where we can see there is brand new ocean floor between these two mountains, and that's what divided the mountains as such. So that's your matching mountain ranges. Next, this is your glacier evidence. So we have evidence of glaciers in places like right here that are extremely that warm, or right here, because that's right on the equator. And the only way we could have it could have been cold enough to have that type of climate is if at one point all of those countries and continents were clustered together down towards the poles. And that's that matches up with a lot of other evidence. So there's your glacier and your mountain evidence. And what we got now? Another brain break. Yay. So this is called the ball toss game. So what you will do to play this is everyone in a second after the video is paused will stand up and you'll form a circle around the room. And so you get the ball and you have to toss the ball to someone, but you have to do this without talking. If somebody talks, then they're out. So if someone starts talking or getting really loud, making any noise like that, then they're out and they need to go back to their seat and sit down. The other time that you're out is if you toss the ball to someone and they miss it, so if they don't catch it, then they're out and they have to sit down. And then you are out if you overly aggressively throw the ball or if you throw it at somebody's head. This is not baseball, so don't do a baseball pitch. It's a ball toss. You are tossing the ball. So don't do anything stupid. If you feel like somebody's being overly aggressive with the ball, you can have them sit out too and they will be out. So go ahead and play that. The last one standing gets candy. Okay, I hope you all enjoyed the ball toss game and had a little bit of fun with that, and hopefully it woke you up. Let's keep going, just a couple more slides. What we're going to look at next is our plate boundaries and the features that are made at these plate boundaries. Plate boundaries are going to be very, very important to make sure that you basically memorize them. I'll show you some things to help you understand why different features are occurring. This is something where a lot of students don't spend time studying, and therefore they can miss like half of the test because they never found out what the features were that went with the boundary. And there's so many questions you can ask around that. So make sure this is something that you do study a lot. So first, let's look at the theory of plate tectonics. With plate tectonics, we're simply saying that there are different plates, and these plates are simply parts of the crust. So that's all that a plate is talking about, is a part of the crust. So a plate equals part of crust. So there's different sections of the crust, parts of the crust, that's what we call plates, and they move. We already looked at that from Continental Drift. So each part in Continental Drift that drifted away, that would be considered its own individual plate. Well, there are two kinds of plates because there's two kinds of crust. You got oceanic crust or oceanic plates, and then you have the continental or the land plates / crust, whatever you want to call it. So the theory of plate tectonics is simply saying that they can move. So we've looked at two theories. The theories of continental drift was saying specifically that all the plates are once together to form a supercontinent. Theory of plate tectonics is just saying that the plates continue to move. So they're very, very similar theories that go together, but they do have two separate names. So as these individual plates move in the past and as they currently are moving right now, they can cause some different things to occur. We have earthquakes because of this plate movement. We have volcanoes because of plate movement, and we also have mountains because of plate movement. If you look outside or you look at the ground below you, technically the crust is always moving. Some form of it, some part of it is constantly going to be moving. It's so slow, we don't notice it ever. If you remember the intro to this whole unit, you had to write down some slow geological processes. And plate movement is one of the slowest processes probably in geology. So you're not going to ever feel the crust moving unless you're at an earthquake, and that's one time where it does speed up, and we'll talk about that later. But that is the theory of plate tectonics. So the individual plates are moving, and because they move, you get earthquakes, you get volcanoes, and you also get mountains. So hopefully you're done writing that down. And I did want to point out one other thing before we move on. If you look at this picture here, it has the red squiggly lines. Those red squiggly lines are showing you the boundaries of the plate. So boundaries of plates are going to move based on where the boundaries are, not where the boundaries of a country is. So for instance, you've probably heard that part of California one day, many million years from now, won't be connected to the U.S. anymore. The plate boundaries don't care that the U.S. has, California connected to it. That doesn't matter. The part of California is on a different plate than the rest of the United States, so it will drift apart. So our plate boundaries sometimes can go through the middle of a country or along the edge of it. But just wanted to point that out before we kept going. So how do the plates move? We know that they move, but what is causing them to move? Well, if you remember, the reason all these plates are moving in the first place is because we have convection in the mantle. The core of the earth is extremely hot, causing the magma to rise up because it's less dense. As it gets closer to the core, that magma cools off and it condenses, going back down, and that's what's creating that convection current. Well, all that the crust is basically layers of rock sitting on top of liquid magma. So if the magma is moving in a circular motion, that's going to mean that the plates are also going to move. They're floating on top of it. So convection is the driving force for all plate movement. And why do we have convection? Because there's unequal heating. And you already know that because we know we have heat transfer anytime there's unequal heating. So looking at this diagram, you have the plates are represented in the green and convection, obviously, the circles. So right here you have the convection current going up this way, and over here you have them going the other way. So at one point, these two plates would have been connected. But because the convection current, the two currents are spinning in opposite directions, it's causing those to split, to divide and go apart. To split. I just cannot write, my goodness. And now you can't see it. It causes them to split. So as those convection currents are going away from one another, it's causing the plates to also go away from one another. These are going towards one another, causing these also to move together. So convection current is what's moving our plates because, again, the magma is not all solid rock. It's moving. And so because the crust is just sitting on top of that moving magma, we are also moving. So that's your causes of plate motion. Hopefully you're done writing, because I don't know what else to tell you. Not write faster or get the notes from someone else. Moving on. That actually we'll do this and then we'll stop the video. Hold on. There we go. Okay, so plate boundary activities. You don't have to write this down, but what we're going to look at in our next set of notes, and we will have an edible lab, so hang in there for that. But you have seismic activity, which will be earthquakes. We're going to look at volcanoes. We're going to look at how mountains are built, and we're going to look at seafloor spreading. And this all has to do with your plate boundaries. So we'll go ahead and end this video, and then this next set of notes, we'll have a fun lab you can look forward to.